Hello. Today we are going to learn the chair and boat conformation of cyclohexane. We know from Beer-Stein theory that cyclohexane, that is this molecule, cannot exist in the planar form because the angle is 120 degree, but all the carbon has sp3 hybridized. So sp3 hybridized carbon always has a tendency to exist at an angle of 190 degree 28 minutes. So it can't exist in this form. So there are two stable conformations of cyclohexane. One is chair form and other is boat form. Now we are going to discuss the two conformations of cyclohexane. One is chair form. The chair form is written in this fashion. This one is chair form of cyclohexane and the other is the boat form of cyclohexane. This one is known as boat form and this one is known as chair form. This one is known as chair form. Okay. Now we are going to discuss the chair conformation of cyclohexane. Look at here. This is the chair conformation of cyclohexane. If you take a close look from this angle, this is actually the chair conformation of cyclohexane. Look at the conformation very closely. This is cyclohexane. Actually, this is the cyclohexane. If you take a look from this angle, you will observe this one like this. So actually this angle, this is not a planar form. These 6 carbon cannot exist in the same plane. They exist in this fashion in the chair form. If you take a look from this angle, this is actually chair. The chair, look at here, this carbon is above the plane, this carbon is below the plane, this one is above, below, above and below and then above. So alternatively the carbons are above the plane, exist above the plane and below the plane. So if we draw the hydrogen atoms here, the hydrogen atoms here, the hydrogen atoms here and the hydrogen atoms here. Look at here, this is actually chair form of cyclohexane. There are some features of this cyclohexane, the chair conformation of cyclohexane. Actually, the 3 carbons are above the plane and these 3 carbons are below the plane. So the bonds, the hydrogen atoms are present above the plane. These are called beta bonds. So this is beta, this one is beta, that is this one is beta, this one is beta, this one is beta bond, this one is beta bond, beta, beta and then beta. So there are 2 types of hydrogens are there. 1, 2, 3. These 3 hydrogens are called axial hydrogens, and 1, 2 and 3. These 3 hydrogen atoms are called equatorial hydrogens. So this hydrogen actually, this is beta axial. This is beta axial hydrogen. Beta axial. This hydrogen is beta equatorial. This hydrogen, this is beta axial. This one is again beta axial. Now this hydrogen, this is beta equatorial. This one is beta equatorial. and this one is beta axial. Okay, so the beta bond 1, 2, 3, 4, 5, 6. These 6 bonds are actually beta bonds. 3 are beta axial and 3 are beta equatorial. And the bonds present below the plane are known as alpha bonds. The alpha bonds. So this is alpha equatorial. This is alpha axial. This one is again alpha axial. This one is alpha equatorial. This one is definitely alpha axial. This one is alpha equatorial. Okay. So there are 6 and 6, 12 hydrogen atoms are present. These 6 hydrogen atoms are called beta hydrogen. 1, 2, 3, 4, 5 and 6. And the 6 hydrogens 1, 2, 3 and 4, 5 and 6. These 6 are axial alpha bonds, present alpha bonds. Okay. Again, I draw this conformation again. Take a close look of the distance between the 2 hydrogen atoms. Look at here. This hydrogen is beta axial and this hydrogen is alpha axial. The distance between these 2 hydrogen, that is beta axial, hydrogen beta axial and hydrogen alpha axial, that is between these 2 hydrogen atoms which are present at the adjacent carbon. So this is your carbon number 1, this is carbon number 2, this is 3, 4, 5 and this is 6. So the distance between these 2 hydrogen atoms 249 picometer. Okay. The hydrogen atoms present, look at here, say this is your equatorial hydrogen and this is your axial hydrogen. The distance between these 2 hydrogen atoms, this is your carbon number 1, that is the distance between hydrogen alpha equatorial and hydrogen alpha axial. Or if you write in this fashion, the distance between these 2 hydrogen and the distance between these 2 hydrogen are equal. That is the distance between alpha equatorial, this is this hydrogen, and alpha axial, this hydrogen, and the distance between hydrogen beta axial and hydrogen beta equatorial. These 2 distances are equal and the distance is, no, this distance is 305, sorry, this is 305 picometer, this is 249 picometer, 305, this is 249 picometer, and lastly 249, this is the distance between these 2 hydrogen. These 2 hydrogen are larger, definitely larger. So this is 305 picometer, this one is 249 picometer. And again the distance between these 2 hydrogen atoms, that is the distance of hydrogen axial, hydrogen beta axial and hydrogen again beta axial, but this hydrogen is present in carbon number 1 and this hydrogen is present at carbon number 3. So I can write this is hydrogen 1, this is hydrogen 3. That is the hydrogen present in attached to carbon number 1 and this hydrogen attached to carbon number 3. The distance between these 2 is 251 picometer. Okay. This is 251 picometer, this is 305 picometer, and the distance between the axial and equatorial hydrogen, this is this one and this one, and again this one and this one. The distance between these two is 249 picometer. This one is 249, this one is 251, and the distance between the hydrogen atoms, this one and this one is 305 picometer. Okay. Now there is a fact that these two hydrogen, that is the hydrogen atoms of carbon number 1 and the hydrogen atom at carbon number 3 and carbon number 5, these three hydrogens are syn axial. That is, there is an interaction between these three hydrogens. This is known as syn diaxial interactions. But look at here, the van der Waals distance in the chair conformation, these three hydrogens are far apart, which is free from this syn diaxial interaction, because the van der Waals radius of hydrogen atom is 120 picometer, and say again the van der Waals radii of this hydrogen is 120 picometer. So 120 plus 120, the van der Waals radius of the summation of the van der Waals radius of these two hydrogen is actually 240 picometer, which is less than the distance between the two hydrogen. So actually these three hydrogens are free from this syn diaxial interaction. But if we substitute this hydrogen, look at here, if we substitute this hydrogen, by say a methyl group, this one is hydrogen, this one is hydrogen. So there is larger interaction. Look at here. If we substitute this hydrogen by a methyl group, so look at here, the hydrogen of the methyl groups and the hydrogen atoms are present at carbon number 3 and carbon number 5 are in close proximity, and the bond rotation around the single bond is possible. So these hydrogens are present in close proximity. So there is an interaction. This is known as syn diaxial interaction. The interaction between the hydrogen atoms of this methyl and the hydrogen atoms here and hydrogen atoms here, this interaction is known as syn diaxial interaction. It is again can be are known as 1,3 syn diaxial interaction. Due to this type of interaction, this molecule can't exist in this form. Later I tell you that this methyl group is actually inverted, is actually flipped to the equatorial position. Okay, look at here. Look at here. Look at here. There is a phenomenon which is known as ring flip. Now, let us see what is flipping of the ring. Look at here. This is the chair conformation of cyclohexane, and this is your hydrogen axial, hydrogen equatorial, hydrogen axial. This is your hydrogen axial, hydrogen equatorial, hydrogen axial, hydrogen equatorial, hydrogen axial. This is again hydrogen axial and then hydrogen equatorial. Look at here. Again, I can back in this fashion. Look at here, this is the chair conformation of cyclohexane. Now there is a phenomenon which is known as a ring flip. What is ring flip? This conformation can be written in this fashion. Now what is the difference between this one and this one? Say I can make you understand in this way that all are hydrogen atoms. Okay. Look at here. What is ring flip? Look at here. This is carbon number 1, this is carbon number 2, 3, 4, 5, 6. Again. Look at here. This carbon is above the plane. Now, if due to the bond rotation, if you keep this side, this carbon in above the plane bond, and this two carbons up, then this two carbon down, and this carbon is up, this carbon is up, this carbon down. Okay, look at here, this conformation is transformed to this one. What happens? Look at again. Look at again, this carbon up, this carbon down. Actually, this was the conformation. Down, this one is up. Okay. Actually, this was the conformation. What is done? This carbon is moved down. This carbon is moved down. This carbon number 1 is moved down. So this carbon is actually transformed to this fashion. This carbon is moved down. Now this carbon number 2 and carbon number 6 is moved up. These two carbon are moved up. Now these two carbon are moved down and this carbon moves up. What happened there? Now this conformation is transformed to this one. That is the conformation, the carbon number 1, the carbon number 1 here, this is your carbon number 1 and now this is your carbon number 1. This is carbon number 2, this is your carbon number 2. That is the axial bond is now transformed into equatorial bonds and the equatorial hydrogen is now transformed to axial hydrogen. In carbon number 2, this hydrogen was equatorial, now this hydrogen becomes axial. And this hydrogen axial now becomes equatorial, and so on, and all hydrogen atoms are changed. That is, very carefully, that look at very carefully, the beta bonds are not changed, the alpha bonds are not changed, the axial bonds are transformed into equatorial and the equatorial bond is transformed into axial. But this one was beta axial, now it becomes beta equatorial. The beta is always beta. The bond which was plane above the plane is always above the plane. But the axial bonds become equatorial and the equatorial bonds become axial. This one was alpha equatorial, now it becomes alpha axial. Okay. This procedure, this phenomenon, this is known as flipping. Now question is, this is known as flipping or ring flip. This is known as flipping or ring flip. This is known as flipping or ring flip. Now the question is, cyclohexane, the chair conformation of cyclohexane exists in which form? It actually exists in both the form. This transformation, this bond rotation is always on. This bond rotation is always occur at room temperature. The energy required for the transformation of this conformation to this one is supplied from the room temperature. The energy required for this interconversion is available from the room temperature. So the molecule always transform from this form to this form and this form from this form. So this is known as actually flipping. Okay, now we can back to our problem. Now in the axial conformation, when this is your methyl cyclohexane, in the methyl cyclohexane there is a syn diaxial interaction. So due to this sort of interaction, the ring flip occurs here. Due to the ring flip, the compound is transformed to this form. Now the methyl goes here, hydrogen is here. This was your hydrogen, this is your carbon number 1, then 2. Now this is your carbon number 1, this is your carbon number 2. The hydrogen atoms are present in this fashion, and so on. Now this syn diaxial interaction is the methyl group is free from syn diaxial interaction here. So in methyl cyclohexane always exists in this form, because in this fashion, when the methyl group is in equatorial position, the syn diaxial interaction is removed, is eliminated. So methyl cyclohexane always exists in the equatorial form. In the same fashion, the same way, if you substitute the hydrogen of cyclohexane by a tertiary butyl group, this is your tertiary butyl group. This is a large group. So there is a very strong syn diaxial interaction between the hydrogen atoms present here and the hydrogen atoms present here. So this molecule always transformed to this equatorial conformation. Sometimes this is written as TBU. This is tertiary butyl group, and this is TBU. That is tertiary butyl cyclohexane always exists in this form. It can't exist in this form because there is a very strong syn diaxial interaction. We can see from the model. This hydrogen is removed. This is your methyl, and if we substitute the 3 hydrogen atoms by 3 methyl groups, 3 large methyl groups. 3 large methyl groups. Look at here. Actually, this one up, down. Okay. Up, down, down, up, and then down. Okay. Look at here. This is actually tertiary butyl cyclohexane. This is your tertiary butyl group. Carbon, methyl, methyl, and methyl. Methyl, methyl, methyl. So there is a very strong interaction between the hydrogen atoms present here and here. So this flipping occurs in this molecule. Due to the flipping, this carbon move down, this 2 carbon move up, this 2 carbon move down, and this 2 carbon move up. Look at here. It always exists in this fashion. Look at here. The interaction present here is somewhat removed, is somewhat eliminated. So tertiary butyl cyclohexane always exists in this conformation. This is your equatorial conformation. Equatorial conformation. Okay. This is all about our chair conformation of cyclohexane. In the next lesson, we just compare between the chair form and the board form of cyclohexane. Thanks a lot. Thanks for watching the video.